Now this is question 3. It's actually, it's question 3 out of the textbook. This one, if you look at your WebAssign questions, you'll find that the questions that I go over in these videos has an order to it. So if you look at the 9 questions on WebAssign, you see that these are the actual questions that they're based on out of the textbook. So question 1 out of section 2.1 out of the textbook is just like question 1 on WebAssign. Question 2 out of the textbook is just like question 2 on WebAssign. Question 3 out of the textbook is just like question 3, and so on. The question 6 is like 4. Question 7 is like 5. Question 6 on WebAssign is just like question 3 repeated. It's almost exactly the same question. Example 1 is like question 8. Example 2 is like question 9. Question 7 is completely different. That's just a totally different line question that's unlike anything else you'll see in this chapter or this section. So let's go over that one. This one asks you to find the equation of a line that goes through this point, 6, 7, and is parallel to a line that goes through these 2 points. So if it's parallel, it means it has the same slope. So if you find the slope of this guy, you can use the slope from this guy with this one. So you do the slope formula with this one and you get 1. So now you use that same slope with your point, 6, 7, and you find the equation of a line that way. Remember, it's y minus y1, m times x minus x1 gives you your slope. And that's how you find the answer for question number 7. Now, question 3 is a pretty hard one because they give you the function y equals 1 over 1 minus x. And they give you a lot of different x values, but they don't tell you the y coordinate. So you have to figure out the y coordinate. So you take each one of these and you plug it into the function 1 over 1 minus x. And when you take each of these x values and plug it into this fraction here, you get these y values. And now you've got a whole bunch of different points, and you're going to use each one of these with p. Okay, so we're going to use Q1, this guy right here, 1.5, negative 2, with p. And we get this answer. And we use this one, Q2, with p, then Q3 with p, and so on. And you get all these numbers here, and eventually you can see that as you get closer and closer to 2 here, and as you get closer and closer to 2 here from above and from below, what happens here is you get closer and closer to 1, and here you get closer and closer to 1 from either side. So it appears that your slope is 1. And if your slope is 1 and you're using the point 2, negative 1 as your p, you just use the slope formula, plug it into the equation of a line, and you can figure out the equation of a line from that one. Y minus y1, m times x minus x1. This idea, by the way, of doing repeated slope calculations over and over again was initially done by the ancient Greeks. Archimedes, I believe, was the first one to look at the unit circle, a circle with radius 1, and he drew a triangle in it with equal side lengths that touched the end, each end point touched the edge of the circle. And back then they were able to calculate the area of a triangle very well. They were very gifted at doing that. So then he took a square, which is just a 4-sided figure, all 4 sides of equal length, and he divided it up into 4 triangles, and he figured out the area of that. Then he took a 5-sided figure where all 5 sides are touching the edge of the circle, and he divided it up into 5 triangles, and he figured out the area of that shape. And as you increase the number of sides, you increase the size of the shape inside the circle, and you get closer and closer and closer to the actual value of the area of the circle. This is actually how Archimedes came across the very first knowledge of the symbol pi. This is where pi actually popped up, because he figured out with the area of a circle, it's pi r squared, right? And if your radius is 1, 1 squared is 1, 1 times pi is pi, so this actually approaches the value 3.1418, 3.1428, and so on. That's where that came from. And so that idea of method of exhaustion, where you increase the number of sides just over and over and over and over again, is the same idea that Newton did back in 1648, just method of exhaustion over and over and over again. You eventually figure out that your answer is approaching a certain number. So again, you got to do the same thing here. Now they give you a whole bunch of x values here. They're talking about the interval from 1 to 2, 1 to 1.5, 1 to 1.1, 1 to 1.01, 1 to 1.0001. They just keep getting closer and closer to 1 here, but it's slightly off from 1. Now these are all x values. You have to figure out the y value. So you take all of these x values and plug them into the function, and the function here is 10t minus 1.86t squared. So these t values you're going to plug into the function and get the y coordinate. Notice your x coordinate is whatever this guy is, and there's your y coordinate. And these are all, other than the first one, this first one is the actual p, the point that you're concerned with. These are all q values that get infinitely closer to the actual value for p. And so you use these different p values with q, and you got to do the slope formula 5 times with each one. Okay, and when you do, you see that it gets closer and closer to 6.28, which is roughly 2 pi. Alright, now if you do the difference quotient like we talked about earlier, you plug in 1 for your x and you plug 1 into the function for your y. Alright, and you crunch that down and you get this number here, this point here. And now instead of 1 you use 1 plus h, some slight increment. It's slightly greater than, slightly larger than 0. And then you plug that into the function itself. Okay, and when you multiply that out, you're going to eventually get to this here. Now how do you get to there? Well, you multiply the 10 times each of those two. You multiply negative 1.86 times all 3 terms inside here. Remember, this is not just a 1 plus h, it's squared, so it's 1 plus 2h plus h squared multiplied by negative 1.86 gives you all this. And you can combine these two constants and these two with an h, and you get this polynomial there. So now you can just take the difference quotient, which is the difference of the y's over the difference of the x's. And notice your 8.14's go away, your 1's and minus 1's go away, and you just got this guy over h, which is what you should typically end up with if you're doing it correctly. And you divide h into each one of those and you get just 6.28 and you get 1.86h. Now if you let h become 1 millionth, 1 billionth, 1 trillionth, this number becomes meaningless and your answer is just going to be 6.28, which is your velocity at instantaneous velocity at t equals 1. Question 7, they give you the points already, and they want you to calculate what's happening at, they're interested in the point, they want p to be the 479.2. So each one of these other guys are your q's, but the 479.2 is your p. And now you do the slope formula with each one of these guys. And you get the velocity, the average velocity over the period from 2 seconds to 4 seconds, velocity from 3 seconds to 4 seconds, from 4 to 5, and from 4 to 6. So the theory is as you get these numbers closer to 4, you'll get closer to your actual instantaneous velocity. This one, it seems like it might be somewhere around 29 or 32. It's not at all clear. Again, they try and do it by brute force, by drawing a picture and measuring each side and just doing the slope or the rise over the run, and they get something close to 30. And so maybe these two numbers are closer to your actual answer. It's not very clear with these numbers what you're going to get. It's better when you look at a problem like number 3, where they're more scientific in the way they use their values for x. So they plug in their p first off is 3, negative 4, their function is 4 over 2 minus x. And here are your different x values, and you're going to plug all these x values into the function to get the y coordinate. Okay, and when you do that, you get you do that down here. Here are your different x values, and you plug them into the function, and you get your different y values. And now you just have to do the slope formula over and over again with each one of these points with 3, 4. So you use the point 3, negative 4 with this first point, then 3, negative 4 with that point, 3, negative 4 with that one, and then with that one. And same thing over here, over here, over here. Okay, so what happens? Well, as you get numbers that are using 2.9 to 2.99999, you get closer and closer to 4, don't you? And then here, when you use numbers that are 3.1, 3.01, 3.0001, you get closer and closer to 3. You get closer, numbers that get closer and closer to 4, just like above. So from below and above, you're getting numbers that approach 4. And so 4 is a very good guess as to what your slope should be here. And if you know the point 3, negative 4, and you got your slope, you can just plug that in, and you get your equation of the line that way. We already talked about number 7. So the basic ideas here, that if you want to find the value of the rate of change or the slope at a given one point on a curve, you have to pick secondary points in order to do the slope formula. And if you pick them wisely so that they get closer and closer to some number, in this case 3, from above and below, you'll see, hopefully you'll see numbers that approach one number, in this case 4. Now there are other examples where this doesn't work, and surprisingly, if you go too far with this method, it will actually backfire on you because your calculator cannot calculate numbers that are infinitesimally small, and you'll start getting, your data will be off, and it won't seem to approach the right numbers. We'll learn in later sections that there's actually some functions where if you try and do this, it doesn't ever settle down to approach some single number. And those are problems where you can't find the slope of the tangent line because the numbers are all over the place. But for question 3 on up to, I think, question 9, you actually have to figure out the y-coordinate of all of your points first, and then just do the slope formula over and over and over again. Now when you do this, this calculations here, I recommend when you're typing in the 2.9 into your calculator, you're going to put parentheses around this as you type this into your calculator. Don't just type in 2.9. Type in 2.9 with 3 zeros after it. 2.9000. And then this one, you don't have to change that because all these other numbers also have 6 decimal places in them. So what you do is when you type that number into your calculator, it's real easy to do the next one. So if you do parentheses negative 4, subtract parentheses negative 4.444444, you got to close parentheses twice, and that's your numerator, divided by your denominator, which is 3 minus 2.9. But you should add 3 more zeros after it, okay, and close it with the parentheses because that's your entire denominator. So now you're going to get an answer there, okay. Now when you go to type in the next one, you can just hit second enter and go back and change that first number from all 4s to 04, 04, 04 by just typing right over the top of that. And then you can change the 2.9 to 2.99 just by changing that second number to a 9. And now you've got your slope formula, and all you have to do is hit enter. And you can do the same thing for the third one. You can just hit second enter and change that 2.9 to 2.999. And you can do the same thing here with this one's 0.004004. And it gives you the next one. So you can calculate the slope very easily doing it that way on your calculator.